Welcome to this course on Relational Database Management. A recent study shows a 70% increase in available positions for data engineering roles. Additionally, data engineers earn an average of $10,000 more annually than data scientists. Relational Databases is a comprehensive and practical course designed to initiate your journey as a junior data engineer. This course is crafted to provide you with essential skills and knowledge in relational database management. To get the most out of this course, you should have a basic understanding of computer science, software development, programming, and cloud computing. The course commences with an in-depth study of the core concepts of relational databases. Throughout the course, you will navigate various relational database products, such as DB2, MySQL, through PHP-MyAdmin, and PostgreSQL, through PGAdmin, gaining insights into their distinctive features and practical applications. In Module 1, you will delve into the fundamental concepts of relational databases. The course will provide you with a solid understanding of the core principles that form the basis of relational database management. Additionally, you will learn about different database systems. This foundational knowledge will set the stage for the subsequent weeks, where you'll continue to build on these concepts and explore hands-on applications in database management. In Module 2, you'll gain hands-on experience in creating tables, loading data, and learning how to design keys, indexes, and constraints efficiently. Module 3 provides a deep dive into MySQL with PHP-MyAdmin and PostgreSQL with PGAdmin, where you'll explore their detailed functionalities. Finally, in Module 4, you'll master the approach to database design, including creating entity relationship diagrams, ERDs, and embark on a final project that synthesizes all of your skills and knowledge. The interactive learning experience includes weekly quizzes designed to reinforce and test your understanding of the course material. These quizzes are assessments and learning tools that enhance your comprehension of key concepts. The course offers a strong foundation and strategic insights into relational databases. It emphasizes the significance of a well-structured relational database in ensuring data reliability, accessibility, and flexibility. The course extensively covers relational database design, including conceptualizing data relationships, effective design strategies, and exploring deployment topologies with associated trade-offs. A key component involves practical application, allowing you to apply your skills in crafting an entity relationship diagram tailored to a specific use case, laying the groundwork for the physical implementation of your database. Hands-on experience forms an integral part of the course, where you will use SQL statements and various RDBMS tools to transform conceptual designs into tangible database elements, including tables, keys, and constraints. Additionally, the course introduces IBM DB2 on cloud as an optional element, providing flexibility in choosing the RDBMS tool that aligns best with your learning path. Engage with interactive videos, comprehensive labs, and a project-driven approach, ensuring a robust and immersive learning experience. Enhance your portfolio and confidently enter the dynamic world of data engineering. To get the most out of this course, view each video, review the readings, complete all hands-on activities, and check your learning with each quiz. We encourage you to participate in the course discussion forums to connect with others taking the course or get help from the course staff. Welcome to the course. We are thrilled to have you on this learning journey. Welcome to Review of Data Fundamentals. After watching this video, you will be able to describe 3 important data structures with examples for each. Identify common file formats for transferring data between systems. Describe relational and non-relational databases. Data pervades every aspect of our surroundings in the rapidly evolving world of information and technology. But how do we define data? Data refers to unorganized information that undergoes processing to make it meaningful. It includes facts, observations, perceptions, numbers, characters, symbols, images, or a combination of these elements. The structure of data plays an important role in determining its efficient management, storage, and analysis. Broadly, we can categorize data into three main types: structured, unstructured, and semi-structured. Let us learn about each of these data structures. Structured data is highly organized and follows a predefined format, typically arranged in tables with rows and columns. It adheres to a strict schema and a rigid structure, ensuring consistency and easy retrieval. Examples of structured data include Excel spreadsheets arrange data into rows and columns, assigning each piece of data a specific cell address. SQL databases that allow data to be stored in predefined tables and columns. Online forms collect customer information by storing each piece of data, name, address, credit card number, in designated fields. In contrast, unstructured data lacks a specific format or organization. It doesn't conform to any predefined rules or sequences, making it challenging to process and analyze using traditional methods. Examples of unstructured data include text files contain free-form text documents without a predefined structure. Media files include images, audio, and video. Web pages' main content, such as text, images, and multimedia, is often unstructured, despite potentially structured elements like HTML tags. Social media content encompasses posts, tweets, and other updates with mixed text, images, and links. The last category we will discuss is semi-structured data. This type of data possesses some organizational properties, but does not adhere to a strict tabular structure. It often employs hierarchical structure or tags to organize information, providing a balance between flexibility and structure. Examples of semi-structured data include JSON files contain arrays and objects, using specific tags or keys to mark different data elements. XML documents define data structure using tags, attributes, and schema. Emails have structured fields, to, from, subject, but unstructured message bodies. Businesses today access a wealth of data from various sources, including traditional databases, flat files, and XML datasets, web scraping, data streams and feeds, social media platforms, IoT devices with sensors. We can hold or transfer data between systems in many different file formats. Common file formats include delimited text files, spreadsheets, language files. Delimited text files. In these files, data resides in rows, with each variable separated by a specific character like a comma or a tab. Delimited files comprise comma-separated variable, CSV, and tab-separated variable, TSV, files. Spreadsheets. In these files, data exists in rows and columns, the same as a table, facilitating easy access and manipulation. A spreadsheet helps to create CSV files. Language files. Language files like Extensible Markup Language, XML, and JavaScript Object Notation, JSON, have set rules and structures for encoding data to send over the internet. After collecting your data, where's the best place to store it? Data repositories actively store, manage, and organize data in a centralized manner, offering a structured framework for efficient retrieval and administration. Two major categories of data repositories are relational databases and non-relational databases. Relational databases consist of structured data stored in related tables. The links between the tables minimize data duplication while preserving intricate relationships. These databases and their supporting systems are collectively known as Relational Database Management Systems, RDBMS. Prominent examples include IBM DB2, Microsoft SQL Server, Oracle, and MySQL. Let us look at the scope of relational databases. Relational databases are primarily OLTP systems used to support day-to-day business activities, such as customer transactions, human resource activities, and workflows. They help in storing high volume of day-to-day operational data that many businesses rely on. Their normalized structure ensures transactional integrity and supports concurrent access for routine operations. OLAP systems include various storage solutions like relational and non-relational databases, data warehouses, data lakes, and big data stores. The system focuses on querying and analyzing large datasets to extract meaningful insights. For example, organizations can leverage data sourced from a customer relationship management (CRM) system for insightful analytics, such as generating sales projections. Now that you know about relational databases, let us explore non-relational databases. They offer flexibility in handling diverse and unstructured data. MongoDB, Cassandra, and Redis represent this category. MongoDB is a document-oriented database suitable for storing and managing semi-structured or unstructured data. In conclusion, data's varied types and structures demand appropriate storage solutions, with relational databases serving OLTP needs, OLAP systems enabling complex analytics, and non-relational databases providing flexibility for diverse data. In this video, you learn that data includes facts, observations, numbers, symbols, images, or a mix. Efficient data management relies on structured, unstructured, and semi-structured categories. Data repositories, including relational and non-relational databases, store and manage data centrally. Relational databases consist of structured data in related tables, used primarily for OLTP. OLAP systems focus on querying and analyzing large datasets for meaningful insights. Welcome to Information and Data Models. After watching this video, you will be able to define the information and data models along with their aspects and differences, describe the relationship between the hierarchical and information models, define the types of data models, discuss the key concepts in database management. Understanding and managing data is fundamental in today's digital landscape. Information and data models are the two key concepts that play an essential role in data organization. Let us define each of these models. An information model represents entities and their properties, relationships, and operable functions abstractly. This conceptual framework provides a high-level and organized view of information, enabling stakeholders to understand the structure and interconnections of data without delving into implementation details. Let's look at the key aspects of information models. They provide a framework for understanding the different types of information an organization uses. The models abstract the complexity of real-world entities and relationships. They encompass broad concepts that may apply across various areas within an organization, and they help understand and define business concepts and rules. A data model operates at a tangible level, serving as the blueprint for translating conceptual information models into practical database structures. It delves into specifics, defining the organization, storage, and retrieval mechanisms for data within a database system. Let us explore the critical aspects of data models. They specify data elements, structures, constraints, and relationships to store. The models contain detailed data and specific, often tailored to a particular database management system, RDBMS. They define the schema, including tables, columns, data types, indexes, and often the relationships between data entities, like foreign keys, and they often involve normalization processes to ensure data integrity and reduce redundancy. Let's discuss the differences between the information and data models. Information models cover fewer details, while data models specify storage or technical manipulation methods. The information model focuses on comprehending broad business concepts and relationships. Conversely, data models gear towards the technical implementation of data storage and querying. Business analysts and stakeholders utilize information models to agree upon concepts without delving into technicalities. Database designers and developers employ data models for constructing database systems. In system development, an information model grasps the essential business information types. Then, the model creates a data model and translates these concepts into a technical blueprint for the database system. The hierarchical model serves as a physical implementation of an information system. This is unlike an information model, which focuses on organizational information without delving into physical or technical specifics. In relationships, an information model conceptualizes without specifying storage, while the hierarchical model physically structures data in a tree-like format. The information model prioritizes high abstraction, focusing on entity relationships for a clear representation of real-world scenarios. Despite alignment potential, the hierarchical model's lower abstraction stores relationships in a database. Challenges arise with its structural limitations regarding many-to-many relationships, potentially leading to data redundancy. Rooted in the historical context of early database systems, the hierarchical model remains linked to the initial phases of information models. Let us now discuss the types of data models. The most common types of data models include the relational model and entity relationship data model. The relational model is the most widely used data model for databases, allowing for data independence. This model stores data in tables, providing logical, physical, and storage independence. The relational data model offers several advantages, including simplicity, flexibility, and ease of use. An entity relationship data model offers an alternative to the relational data model. The entity relationship model suggests conceptualizing a database as a collection of entities and objects existing independently within the database. Using a simplified library database as an example, this figure illustrates an entity relationship diagram, ER diagram, representing entities and their relationships. Converting an ER diagram into tables is easy. Entities and attributes are the building blocks. Entities, like rectangles, have attributes, data elements, represented by ovals. In the library, for example, books and authors are entities. For an entity like author, the ER diagram shows attributes like last name, first name, email, and so on. This entity becomes a table in the database with attributes as columns. Advancing through the simplified library database process involves identifying entities such as borrowers, various copies of each book, and copies of books out on loan. The final ER diagram delineates each entity, corresponding to a table in the database. Let us learn about the few concepts that help ensure adaptability and efficiency in database management. These three essential concepts are logical data independence, physical data independence, and physical storage independence. Logical data independence enables modifications to the database structure without impacting user data access, such as altering data types or adding fields. Physical data independence allows tweaking the internal database organization, like changing data storage types or indexing strategies, without affecting user views or applications. Physical storage independence allows moving or reorganizing data on physical storage devices without impacting application programs processing the data. In this video, you learn that information models provide abstract representations of entities and relationships. Key aspects of information models include abstraction, broad concepts, and business rule definitions. Data models serve as blueprints for practical database structures. The hierarchical model is a physical implementation of an information system. Logical data independence, physical data independence, and physical storage independence are crucial concepts in database management. Welcome to ERDs and Types of Relationships. After watching this video, you will be able to describe Entity Relationship Diagram, ERD, and its fundamental components. Identify the difference between one-to-one, one-to-many, and many-to-many relationships. An ERD is a visual representation that illustrates the relationships and interactions between entities in a database. It showcases the logical structure of a database system, displaying entities and the relationships between them as lines connecting these boxes. Let us now explore the fundamental components that form the structure of a relationship. These include entities, relationship sets, and crow's foot notations. Entities in ERDs represent people, objects, or concepts that store data in a database. They serve as fundamental building blocks, depicted as rectangles in ERDs, and contain attributes describing specific properties. Entities form the basis for relationships within the database model. Relationship sets illustrate how entities are interconnected or associated with each other within a database. They represent the connections between different entities, showing how instances of one entity type relate to instances of another entity type. Crow's foot notation is a visual representation to indicate the relationship between entities in a database. It employs symbols to signify the nature and quantity of relationships between entities. These symbols provide a clear depiction of whether the relationship is one-to-one, one-to-many, or many-to-many, helping in the design and understanding of complex databases. There are different techniques for representing relationships. A rectangle represents entity sets. A diamond represents relationship sets, with lines connecting associated entities. The crow's foot notation employs symbols such as the greater than symbol, the less than symbol, and vertical lines to signify the nature and quantity of relationships between entities. In this example, the entity book is shown in a rectangle, and the attributes are shown in oval. Attributes are certain properties of that entity, for example, title, edition, year, price, and so on. Each attribute connects to exactly one entity. Let's now see how the ER diagram appears for the author entity. The entity author has attributes such as last name, first name, email, city, country, and author ID. Let's explore how the entities book and author relate to each other. A book requires at least one author but can involve up to 2 authors or even more. Similarly, an author can write 1, 2, or multiple books. In both scenarios, a definitive relationship exists between the book and the author. In this scenario, the relationship set is named authored by. Each book is written by a single author, denoted by the thick lines connecting the entities. It represents a one-to-one relationship, implying that each entity in the set is engaged in at least one and precisely one relationship. The diagrams only feature entities, as including attributes might clutter the diagram. When multiple authors contribute to a book, it can be depicted using crow's foot notation using a less than symbol. The symbol signifies that one book entity is participating in multiple relationships within the set. It is termed as one-to-many relationship. The relationship can also be viewed as a many-to-one, signifying that multiple authors contribute to a single book. To represent many authors writing many books, use the greater than and less than symbols on either side of the relationship set. The scenario is termed a many-to-many relationship. Multiple relationships involve each entity in the entity set. It includes scenarios where many authors author many books. In this video, you learn that an ERD is a visual representation that illustrates the relationships and interactions between entities in a database. The fundamental components that form the structure of a relationship include entities, relationship sets, and crow's foot notations. In a one-to-one relationship, each entity is linked to just one instance of another entity. In a one-to-many relationship, an entity is linked with multiple instances of another entity. In a many-to-many relationship, multiple instances of one entity are linked with multiple instances of another entity. Welcome to Mapping Entities to Tables. After watching this video, you will be able to define Entity Relationship Diagram, ERD, and Relational Database, identify the key components of ERD, outline the steps involved in mapping entities to tables, describe the best practices for relational database design. An ERD is a graphical representation of the entities and the relationships between them in a database. It is a modeling technique used in database design to represent the structure of a database system visually. The primary components of an ER diagram include entities, attributes, and relationships. Here are the key components of an ERD. Entities represent real-world objects, concepts, or things that store and manage data. Rectangles in an ER diagram depict these entities. In this example, book represents an entity. Attributes represent the characteristics associated with an entity. Ovals inside the entity rectangle depict these attributes. In the given example, ISBN, title, author, and published year are all attributes. Relationships illustrate how entities interrelate. Let's introduce another entity in the example, say, author. A relationship could be that an author writes a book, represented by a line connecting the author and book rectangles in the ER diagram. The relational database model provides a well-defined framework for managing and manipulating structured data. In a relational database, you organize data elements in a table. Relationships between the tables depend on common fields. To design a relational database, begin with an ERD and then map the ERD to the tables in a database. The illustration utilizes an ERD for the book entity as an example. The entity book becomes a table with the same name, book. This step provides the structure for the rows and columns. However, the table is still empty. It doesn't contain actual data. The next step involves translating attributes into the table. When translated to a table, the attributes of an entity become columns in that table. For example, if book had attributes ISBN, title, and author, these become columns in the book table. The final step is to add data values to the table's columns. You can add the relevant data as shown in the table. The step completes transforming a conceptual entity into a tangible table with specific data. You will follow similar steps for other entities. For example, transform the entity author into the table and translate the attributes into columns. Adding data values into the columns completes the table. Let us now discuss the best practices for designing a relational database. The best practices involve primary key designation, data validation, default values, using views, concurrency control. Let us discuss the best practices in detail. Primary key designation. A primary key is an exclusive identifier allocated to each entry in a table. Designate a primary key for the book table, such as book ID, to identify each book in the database uniquely. Data validation. Implement data validation mechanisms to ensure the accuracy and consistency of the data entered into the database. The step may involve checks for data, types, ranges, and formats. For example, ensure that the published year attribute for the book entity only accepts numerical values within a specified range. Default values. Consider assigning default values to certain columns to streamline data entry and enhance the records. For example, set a default value of unknown for the author column in the book table to handle cases where the author's information is not available. Use of views. Utilize views to present a customized and simplified data perspective, especially for complex queries or reporting purposes. For example, create a view that combines information from the book and author tables to present a comprehensive list of books and their authors without showing the underlying complexity. Concurrency control. Implement concurrency control mechanisms to manage multiple users' access and modifications to the database concurrently. This step helps prevent data inconsistency and conflicts. For example, include a last modified timestamp in the book table. In this video, you learn that an ERD is a graphical representation of the entities and the relationships between them in a database. ERD components include entities, attributes, and relationships. Relational databases organize data into tables with relationships based on common fields. Entities become tables with the same name, and attributes become columns within those tables. Adhering to best practices in relational database design is crucial for ensuring the efficiency and maintainability of the database system. Welcome to Data Types. After watching this video, you will be able to describe data type with the help of an example, explain varchar, its usage, and the key factors to consider when using it. Identify some common data types. Explain the advantages of employing suitable data types. A database table signifies a singular entity, with its columns symbolizing the attributes of that entity. For example, a table named Book could contain columns for the title, published date, and the number of pages that they contain. The information entered in each column should always be of the same sort or type of data. In this example, the title column should contain textual data. The published date column should contain a date, and the pages column should contain a number. We can use this idea to define the type of data or data type that a column can store. The data type you assign to a column controls the data the column can store. For example, a text column can contain alphanumeric data, but a date column can only contain dates in a valid date format, and a numeric column can only contain numbers. When working with databases, understanding various data types and their specific attributes is crucial for effective data management. One common data type is varchar. The key feature of varchar is that it can hold varying lengths of characters up to a specified maximum length. Let us now take a look at this example. Varchar 100 allocates storage for a string of up to 100 characters. If you store a string of length 50, it only uses the space needed for these 50 characters, not the full 100. Let us now explore some aspects to consider. The first one is efficiency. By allocating only the necessary space, varchar types can be more space efficient compared to fixed-length types like char. The second one is flexibility. They are ideal for storing strings whose lengths might vary significantly, such as names, addresses, or descriptions. Different database systems may have variations in how they handle common data types. These include date, time, float, or decimal. Most databases have date for storing dates, year, month, day, and time for time of day. They also usually support a date-time or timestamp type for a combination of date and time. Example, in MySQL, date format is year, month, day, while timestamp includes both date and time. Float and decimal are numeric data types used for numbers with fractional parts. Float is a floating point number with approximate precision. It's used when exact precision isn't necessary. Decimal, on the other hand, is used for exact arithmetic calculations. It's more suitable for financial calculations where precision matters. Example, in SQL Server, float 24 represents a floating point number, whereas decimal 5,2 stores a number with 5 total digits, 2 of which are after the decimal point. Integer types, big int, small int, store whole numbers. Each type has a different range. For instance, int typically stores numbers from -2,147,483,648 to 2,147,483,647. Binary data type stores binary data, like images or files, and types like binary large object, blob. These types store data as a sequence of bytes, which is ideal for non-textual data. Char is another character data type used for fixed-length strings. Unlike varchar, char always uses the specified number of characters, padding the value with spaces if necessary. Understanding the nuances of different data types and their implementation across various database platforms is key to efficient database design and data storage. Always choose the data type that best suits the nature of your data and the requirements of your database system. Using the appropriate data type provides many advantages. Some of these are, when you define the data type a column should hold, you avoid inserting incorrect data into that column. When date, time, and numeric data are correctly typed, you can accurately sort that data. Similarly, you can accurately select ranges of data when it is correctly typed. And you can perform numeric calculations on typed data, for example, calculating an order's total cost. In this video, you'll learn that data types define the type of data that you can store in a column. Varchar, an abbreviation for variable character, is a data type that stores character strings. There are many different data types for all kinds of data. Using the correct data type for a column has many advantages. Welcome to Relational Model Concepts. After watching this video, you will be able to identify various set operations, describe the properties and aspects of relations, explain the difference between a relational schema and a relational instance, define relational terms such as degree and cardinality. The relational model introduced in 1970 offers a powerful approach to organizing and understanding data. It centers around two fundamental concepts: sets and relations. Let us define each of these terms. A set is a collection of unique elements without a specified order, comprising items of a similar type. Usually, curly braces denote sets, with the elements listed inside or described using set builder notation with a condition. Sets play a critical role across various disciplines in modern mathematics, influencing algebra, geometry, and probability. Here are some of the basic ideas and operations associated with sets. Membership. Lowercase a is an element of uppercase A. If an object A is an element of set A, denoted by element A, subset A is a subset of B. A set A is a subset of a set B if every element of A is also an element of B by A subset B. Union, A union B. The union of two sets, A and B, is the set of elements that are in A, in B, or both, denoted by A union B. Intersection, A intersection B. The intersection of two sets A and B is the set of elements that are in both A and B, denoted by A intersection B. Difference: A/B or A-B. The difference between two sets, A and B, is the set of elements that are in A but not in B. Empty set. The empty set, denoted by curly brackets or the null sign, is a unique set having no elements and is a subset of every set. Additional set concepts include power set. The power set of A is the set of all possible subsets of A, including the empty set and A itself, denoted by P parentheses A. Universal set. The universal set, typically denoted by U, is the set that contains all objects under consideration, and all other sets are subsets of it. Disjoint sets. Two sets are disjoint if they have no element in common. Venn diagrams. These diagrams are visual representations of logical relations between sets. In addition to sets, the study of relations is essential. It is a mathematical concept based on the idea of sets. Relations describe connections between elements of sets and are crucial in set theory and logic. Common types include binary relations and ordered pairs. A binary relation establishes a connection between two elements. For instance, the less than relation illustrates the relationship between two numbers, like 3 is less than 5. Ordered pairs, a subset of the Cartesian product A times B, represent a binary relation on sets A and B, denoted as parentheses A, B parentheses. Relations demonstrate various properties contributing to their significance in mathematical analysis. The first property is reflexivity. A relation exhibits reflexivity when each element relates to itself. For instance, the equality relation, equal, exemplifies reflexivity as A equals A for any element A. The second property is symmetry. The property characterizes a relation of symmetric if, whenever element A relates to B, B also relates to A. The is a sibling of relation serves as an example of symmetry. The next property is transitivity, which signifies that if element A is related to B and B is related to C, then A is also related to C. The less than relation displays transitivity. If A is less than B and B is less than C, then A is less than C. The last property is antisymmetry. It defines a relation as antisymmetric when A relates to B and B relates to A, necessitating A to be equal to B. The less than or equal to relation demonstrates antisymmetry. A relation consists of two essential components: the relation schema, specifying the structure, and the relation instance, representing the actual data. A relation schema specifies the name of a relation and the name and type of each of the columns, which are the attributes. In this context, the entity author serves as an example. Author is the name of the relation. Author_ID is an attribute which can hold the data type char, which is a character string of a fixed length. Likewise, last name, first name, email, and city have the data type varchar, which is a character string of a variable length. The last attribute, country, also has a data type of char. This constitutes the relation schema. The relation instance embodies the real-world data stored in the table. A relation instance consists of rows and columns. The columns in the instance correspond to attributes, and the rows represent tuples, which are individual records. To comprehend the relational model, let us understand key concepts like degree and cardinality. Degree represents the number of attributes or columns in a relation. Cardinality reflects the number of tuples or rows. In the given example, the degree is 6, signifying the number of columns, while the cardinality is 5, indicating the count of tuples or rows. In this video, you learn that sets are collections without a specified order. Key set operations including membership, subsets, union, and intersection aid in understanding logical relations between sets. Relations describe connections between set elements, impacting set theory and logic. Common types of relation include binary relations and ordered pairs. A relation consists of two essential components, the relation schema and the relation instance. Degree indicates the number of columns, and cardinality is the count of row. Welcome to Database Architecture. After watching this video, you will be able to Describe some common deployment topologies. Recognize the advantages of deploying databases in cloud. The deployment topology is the arrangement or configuration of the hardware, software, and network components in a system or application deployment. The choice of deployment topology depends on factors such as scalability, performance, reliability, and the nature of the application. Here are some common deployment topologies: single-tier architecture, client-server architecture or two-tier database architecture, three-tier architecture, and cloud-based deployment. Let's explore these topologies in detail. A single-tier architecture deploys all components of an application, including the user interface, application logic, and data storage on a single server or machine. In this configuration, the application's entire stack operates within the same environment. Let's now discuss client-server architecture, also referred to as a two-tier architecture. The architecture represents a deployment topology that divides the application into two distinct layers: a client layer, responsible for the user interface, and a server layer, managing the application logic and data storage. In this scenario, a remote server hosts the database, and users usually access it from client systems, commonly through a web page or local application. In two-tier database setup, the database server and application function are in distinct tiers. The client-tier application establishes a connection to the database server through a database interface, such as an API or framework, depending on the programming language used to write the application. This interface communicates with the database server through a database client or API installed on the client system. The server's database management system software, RDBMS, comprises several layers, broadly categorized as data access layer, database engine layer, database storage layer. Communication between the database interface and server occurs through a database client or API installed on the client system. The data access layer server provides interfaces for various client types, encompassing standard APIs like JDBC and ODBC, command line processor, CLP interfaces, and vendor-specific or proprietary interfaces. Additionally, the database server incorporates an engine responsible for compiling queries, retrieving and processing data, and delivering the result set. In scenarios involving multiple users, the introduction of a middle-tier or application server layer often occurs between the application client and the remote database server, forming a three-tier architecture commonly deployed in production environments. Most production environments usually restrict access to database servers, except administrators. This limitation arises for several reasons. A primary concern is security. Database servers contain sensitive data, so limiting access to authorized personnel is important to protect against unauthorized data access or modification. The next concern is performance optimization. Database servers are often critical components of applications, so it is important to avoid overloading them with unnecessary traffic. Lastly, maintainability is crucial, and administrators, with their training and experience, are entrusted with making changes to the database schema or data to avoid disrupting the application. In a three-tier database architecture, the application presentation layer and business logic layer exist in different tiers. The presentation layer serves as the user interface, accessible through various platforms like desktop applications, web browsers, or mobile apps. The client application interacts with an application server via the network. The application server encapsulates both the application and business logic, establishing communication with the database server through a database API or driver. For instance, in an internet banking app scenario, the client application, such as a mobile phone, connects to a banking application server, which further communicates with the bank's database servers, storing users' account data. Let's now learn about cloud topology. Using the cloud to deploy databases is becoming increasingly popular. In cloud deployment, the database resides within a cloud environment, offering the many advantages inherent to cloud-based services. Therefore, it eliminates the need to download or install database software locally and ongoing maintenance of supporting infrastructure. Cloud-based databases are easily accessible to users from anywhere, at any time, and with only an internet connection required. Client applications and users interact with the database through an application server layer or interface situated within the cloud environment. The flexibility of cloud deployments make them suitable for a wide range of purposes, including development, testing, and full-scale production environments. In this video, you learn that deployment topology involves organizing hardware, software, and network components. A single-tier architecture deploys all components of an application on a single server or machine. In a two-tier database setup, the database server and application operate in separate tiers. In a three-tier database architecture, the application presentation layer and business logic layer exist in different tiers. Users with an internet connection can access cloud-based databases from anywhere. Welcome to Distributed Architecture and Clustered Database. After watching this video, you will be able to describe common types of database architecture along with their benefits, describe some techniques for managing data and optimizing performance. In our exploration of database architectures, we've primarily focused on single server configurations. However, for critical or large-scale workloads where high availability or scalability is important, Relational Database Management Systems, RDBMSs, offer distributed architectures. These distributed database architectures involve clusters of machines interconnected through a network, distributing data processing and storage tasks. The approach brings about notable benefits, including enhanced scalability, fault tolerance, and overall performance improvements. Let's now discuss the types of database architecture. The common types of database architecture include shared disk architecture, shared nothing architecture, and combination and specialized architectures. Shared disk architecture involves multiple database servers processing workloads in parallel. Each server establishes a connection to shared storage and communications with other servers using high-speed interconnection. The shared disk architecture also facilitates the effective distribution of workloads, ensuring scalability as the demand for processing power grows. In the event of a server failure, a mechanism is in place to reroute clients seamlessly to other servers, maintaining high availability and minimizing service disruptions. Let's now learn about shared nothing architecture, which utilizes either replication or partitioning techniques. The approach allows for the effective distribution of client workloads across multiple nodes, promoting parallel processing and efficient resource utilization. One of the key advantages lies in enhanced fault tolerance, achieved by rerouting clients to alternative nodes in the event of a server failure. Certain distributed database architectures employ a combination of shared disk, shared nothing, replication, or partitioning techniques. Additionally, they integrate specialized hardware components to achieve specific goals related to availability and scalability. Now that you know different types of database architectures, let's explore some techniques for managing data and optimizing performance. Some of the common techniques include database replication, database partitioning, and sharding. Database replication is a technique that involves copying changes from one database server to one or more replicas. This process distributes the client workload across servers, leading to improved performance. When the replica resides in the same location, we call it a high availability HA replica. If the primary database server experiences a failure due to software or hardware issues, the system redirects clients to HA replica. To mitigate broader disasters, organizations establish replicas in geographically distributed locations. This guarantees that during instances of complete data center outages, be it due to power loss, fire, earthquake, or flood, clients can be rerouted to disaster recovery replicas. An alternative strategy involved partitioning tables with substantial data into logical segments, each containing a subset of the overall data, e.g., sales records for different quarters. This technique, known as sharding, places these partitions on separate nodes in a cluster. Each shard possesses its compute resources, processing, memory, and storage to operate on its specific subset of data. When a client issues a query, it is processed in parallel across multiple nodes or shards, and the results from different nodes are synthesized and returned to the client. As data or query workloads increase, Additional shards and nodes can be seamlessly added to the database cluster, facilitating increased parallel processing and improved overall performance. Database partitioning and sharding are particularly prevalent in handling data warehousing and business intelligence workloads that involve extensive volumes of data. In this video, you learn that RDBMSs offer distributed architectures for critical or large-scale workloads. Shared disk allows parallel processing with mechanisms for high availability during server failures. Shared nothing employs replication or partitioning for optimized performance. Database replication involves copying changes from one database server to one or more replicas. Sharding involves placing partitions on separate nodes, facilitating increased parallel processing and improved overall performance. Welcome to Database Usage Patterns. After watching this video, you will be able to identify the major categories of database users and their use cases for accessing the database. Explain the interfaces and tools used by different types of database users. Different job roles use different tools to access databases. Three primary classes of database users include data engineers and database administrators, data scientists and business analysts, application developers. Let's discuss these roles along with the tools utilized by them. The first key users of databases include data engineers and database administrators, DBAs. Their main activities involve engaging with databases for administrative purposes, which include the establishment and supervision of database objects, implementation of access controls, and the monitoring and enhancement of performance. Their primary focus is on creating a solid foundation for storing and managing data efficiently. Data engineers and database administrators employ the following mechanisms for performing their tasks: graphical user interfaces, GUIs, or web-based management tools, command line interfaces and utilities, application programming interfaces, APIs. Let's explore the utility of these mechanisms. GUIs, or web-based management tools, serve as common means for interacting with databases. Databases typically offer graphical tools, web-based interfaces, particularly for cloud databases, and mobile applications. If vendor-provided tools lack sufficient functionality or user-friendliness, users may turn to third-party or specialized alternatives. For example, Oracle SQL Developer is a graphical tool provided by Oracle for database management. Command line interfaces and utilities continue to play a crucial role despite the prevalence of GUI tools. Proficiency in command line usage remains valuable for certain tasks. While using these tools, users can issue database commands directly or utilize interactive shells for efficient command line interactions. Let's explore examples of each. Command line interfaces may involve issuing straightforward database commands directly from the terminal, such as db2 create database sample, MySQL dump Sequila greater than Sequila.sql. Alternatively, interactive command line shells like SQL Plus for Oracle or DB2 CLP can be utilized as demonstrated by db2 greater than connect to sample. Furthermore, SQL scripts and batch files executed from the shell provide additional means of interacting with databases. Databases often incorporate programmatic interfaces or APIs designed for administrative tasks, accessible from applications and tools created by data engineers or third parties. Users commonly employ APIs in situations requiring automated or programmatic access for tasks like creating and managing database objects, setting access controls, and monitoring performance. Other key users include data scientists and business analysts. These users engage with databases for data analysis, insight derivation, and data-driven predictions. Their typical data access patterns involve reading from existing data sources, occasionally necessitating the creation and population of database objects, especially in their sandbox environments. Frequently employed tools for tasks in data science and machine learning encompass Jupyter, RStudio, Zeppelin, SAS, and SPSS. Reporting, dashboarding, and business intelligence tasks utilize tools such as Microsoft Excel, Microsoft Power BI, Microsoft Tableau, and MicroStrategy. Both data science and business intelligence tools interact with relational databases through SQL interfaces and APIs, often abstracting away the direct use of SQL. Additionally, users may opt for SQL query tools for ad hoc querying, commonly provided by databases or available as third-party solutions compatible with various database systems. The last users we will discuss are application developers. They seldom access databases directly. They create applications that can require both read and write access to databases. Developers use programming languages such as C++, C#, Java, JavaScript, .NET, PHP, Perl, Python, and Ruby to write applications. The programming languages communicate with the database through SQL interfaces and APIs like ODBC and JDBC. Some databases, especially cloud-based ones, also include REST APIs for accessing data. Although programming applications using these lower-level APIs is feasible, it is worth noting that this was the conventional approach for developing applications in the past. Nowadays, most programmers opt for Object Relational Mapping, ORM, frameworks when working with databases. ORM frameworks are tools in software development that facilitate the interaction between a relational database and an object-oriented programming language. They are user-friendly and can conceal the intricacies of the underlying relational database and SQL. Examples of popular ORM frameworks include Active Record in Ruby applications, Django in Python, Entity Framework in .NET, Hibernate in Java, and Sequelize in JavaScript. In this video, you'll learn that databases cater to various user roles, including data engineers and DBAs, data scientists and analysts, application developers. Data engineers, DBAs, manage databases using GUIs, command line interfaces, and APIs for administrative tasks. Data scientists, analysts, leverage tools like Jupyter, RStudio, and SQL interfaces for analysis, while BI tools like Power BI and Tableau abstract SQL interactions. Application developers use programming languages and ORM frameworks for application development. Welcome to Introduction to Relational Database Offerings. After watching this video, you will be able to summarize the history of relational databases, identify popular open source and commercial databases, discuss the popularity of open source and commercial databases in the past decade, discuss the rise in popularity of cloud databases. Let's start in the 1960s. In the 1960s, IBM and American Airlines created the IBM Sabra Seat Reservation System, the first product recognizable as a relational database. In the early 70s, Edgar F. Codd listed 12 rules to define relational databases. In 1976, Peter P. Chen introduced the Entity Relationship (ER) database model. By the late 70s, Ingres from the University of California, Berkeley, and System R from IBM San Jose were operational. The 1980s marked the commercial success of relational database systems, with DB2 becoming IBM's flagship product and structured query language, SQL, emerging as the standard query language. Towards the late 80s, an IBM workgroup designed a distributed relational database architecture facilitating network-connected databases to collaborate for SQL requests. By the early 1990s, new client tools for application development, including Oracle Developer, Power Builder, and VB, and tools for personal productivity like ODBC, Excel, and Access were becoming popular. In the late 1990s, the database industry experienced exponential growth. Average desktop users began to use client-server database systems to access computer systems that contain legacy data. Some of the most popular relational databases included giants such as Oracle, Microsoft SQL Server, and IBM DB2. In the 2000s, open-source databases gained momentum, replacing commercial counterparts. MySQL, PostgreSQL, and other systems introduced open-source solutions to the Internet. The 2010s saw the popularity of cloud databases soar, with the leading players in the industry being Amazon RDS, IBM DB2 on cloud, Microsoft SQL Azure, and Oracle Cloud. Large corporations developed and maintained the most popular relational database systems for years. They utilized the resources and talent to create sophisticated, fully featured solutions that catered to industry needs at the time. These commercial relational database management systems, RDBMS, played a pivotal role in this landscape, as organizations wanted licensed solutions that offered reliability, scalability, and comprehensive features. Commercial licenses continue to drive the popularity of these relational databases, with Oracle, Microsoft SQL Server, and IBM DB2 leading the market. Most large corporations offer both on-premises and cloud-based versions of their products. In the late 2000s, the popularity of open-source licensing for relational database systems such as MySQL, PostgreSQL, and SQLite experienced a surge in popularity. Open-source licensing is software licensing that allows the source code of a computer program to be free and available to the public. The fundamental principles of open-source licensing include allowing users to view, modify, and distribute the source code. These principles foster collaboration and transparency within the software development community. Examples of popular open-source databases include MySQL, which Oracle produces and offers under the General Public License version 2. PostgreSQL is produced by the PostgreSQL Global Development Group and offered under the free, open-source, permissive PostgreSQL license. SQLite was created by Dwayne Richard Hipp and provided under a public domain license. Let us now discuss the popularity of commercial and open-source licensing. Industry analyst DB Engines conducts a monthly assessment of the popularity of various database products. The DB Engines ranking, which evaluates the popularity of relational database systems, relies on a multifaceted approach. The DB Engines ranking bases its assessment on the following: mentions on websites such as Google and Bing, general interest, Google Trends, occurrence of technical discussions on platforms such as Stack Overflow and DBA Stack Exchange, number of times mentioned in job postings on Indeed and Simply Hired platforms, mentions on LinkedIn profiles, other social media mentions. As of February 2021, here are the 10 most popular relational database systems: Oracle, MySQL, Microsoft SQL Server, PostgreSQL, MongoDB, Redis, Elasticsearch, IBM DB2, SQLite, Microsoft Access. In the last decade, there has been a significant shift in the preference for licensing models, impacting various software categories, including relational databases. The ascendancy of open-source licensing has been remarkable, surpassing the declining popularity of commercial licensing. Both licensing models share an equal distribution, with open source slightly leading at 50.1%. A 2023 DB Engine study found that open source systems account for 55.3% of the total DB Engine popularity score, up from 35.5% in 2013. This trend reflects the growing acceptance and adoption of open-source relational databases within the software landscape. A cloud database is a service constructed and accessed through a cloud platform, offering functionalities like traditional databases while leveraging the added advantages of cloud computing. Over the past decade, the popularity of cloud databases has more than doubled, and this upward trajectory is expected to persist. By 2025, experts predict that 80% of all databases will deploy on or migrate to a cloud platform. This forecast emphasizes the growing significance of cloud-based solutions in the database landscape and reflects the continuous shift towards leveraging the scalability and efficiency offered by cloud computing. The primary driver for the consistent growth in the popularity of cloud databases is the increasing adoption of the software as a service (SaaS) model, enabling organizations to leverage cloud benefits like enhanced scalability. Cloud databases facilitate processing extensive data volumes essential for robust data analytics. Cloud platforms provide built-in data backup and disaster recovery solutions, guaranteeing critical data protection. Some of the leading cloud databases include Amazon DynamoDB, Microsoft Azure Cosmos DB, Microsoft Azure SQL DB, Google BigQuery, and Amazon Redshift. In this video, you learn that in the 1960s, IBM and American Airlines created the IBM Sabra Seat Reservation System, the first product recognizable as a relational database. Relational databases are available with commercial licenses from companies like IBM, Oracle, and Microsoft. Open source licensing is software licensing that allows the source code of a computer program to be free and available to the public. The popularity of open source relational databases has risen in the past decade. Cloud databases offer increased scalability and data accessibility.
Welcome to DB2. After watching this video, you will be able to describe DB2, its histories and features, list various DB2 products and deployment options, describe DB2 on cloud and its plans, explain how you can work with DB2 on cloud, describe DB2 high availability options, and describe DB2 scalability with partitioning. Database 2, or DB2, was first released by IBM in 1983 and was an early example of a relational database management system. This first release ran on IBM mainframe computers, but over the years, different versions were developed to run on many other platforms, including OS/2, Unix, Linux, and Windows. After some time, the product was rewritten to use the same codebase across the multiple operating systems so that you can easily port applications accessing DB2 data from one operating system to another. After many iterations of the offering across many platforms and with enhanced functionality, today DB2 is a whole suite of database management products, including DB2 Database, DB2 Warehouse, DB2 on Cloud, DB2 Warehouse on Cloud, DB2 Big SQL, and DB2 for ZOS. There are many ways to evaluate these products. You can use DB2 Database Community License for free with a 100 GB data limit, or you can download a free Docker image of DB2 Database. You can also use the free Lite plan of DB2 on Cloud for development and evaluation purposes on IBM Cloud. DB2 Warehouse Enterprise Edition and DB2 Big SQL are available in no-cost trial editions. You can use DB2 Warehouse on Cloud for free up to 1 GB of data. The DB2 products all use AI-powered functionality to simplify the management and querying of your data, both on-premises and in cloud environments. You can use machine learning algorithms to improve the efficiency and performance of queries. The column store feature to improve performance and reduce overheads for analytic workloads by directing queries to specific columns rather than processing an entire data table. And the data skipping feature to reduce overheads by automatically avoiding processing data that is not required in a particular query. The common SQL engine across all the DB2 family means that you can write a query once and be sure it will work with other products in the family. This simplifies migration of applications between products and platforms. The support for all data types, relational, structured, and unstructured, means you can access all of your corporate data to make better business decisions. And the DB2 replication functionality enables you to implement high availability and disaster recovery solutions. DB2 provides scalability in a number of ways. For short peaks, you can extend on-premises storage and power levels onto hosted cloud deployments, and you can independently scale power and storage in a managed cloud deployment to only use and pay for extra resources when you need them. Or in DB2 Warehouse, you can use the database partitioning feature to transparently split data across partitions and servers to maximize the compute power available and enable massively parallel processing. The DB2 family provides you with a range of data management products to work with data on-premises or in the cloud. DB2 Database is a powerful enterprise-ready on-premises RDBMS optimized for OLTP. It is supported on Linux, Unix, and Windows, and provides performance, high availability, scalability, and resilience. DB2 Warehouse is an on-premises data warehouse that provides advanced data analytics, massively parallel processing, and machine learning. DB2 on Cloud is a fully managed cloud-based SQL database which provides similar features to DB2 database: performance, high availability, scalability, and resilience. And DB2 Warehouse on Cloud is a fully managed, elastic, cloud-based data warehouse that provides similar features to the on-premises DB2 warehouse. You can deploy both of the cloud-based products on IBM Cloud and Amazon Web Services. DB2 Big SQL is an SQL on Hadoop engine that provides massively parallel processing and advanced querying functionality. You can use it to query a range of data sources, including Hadoop HDFS and Web HDFS, RDBMS, NoSQL, and other object stores. You can integrate it with Cloudera Data Platform or use a service on IBM Cloud Pak for data. And finally, DB2 for ZOS, an enterprise data server for IBM Z. It provides a mission-critical data solution with integration for analytics, mobile, and cloud that supports thousands of customers and millions of users. Cloud Pak for Data is a fully integrated data and AI platform that you can use to work with and manage all of your data. It runs on Red Hat OpenShift in a container, so you can deploy it on any private, public, or hybrid cloud. Using Cloud Pak for Data, you can connect to DB2 or any other data source wherever it may be stored. Use the Watson Knowledge Catalog to organize your data. Work with a range of analytics services to gain insight on your data. And use Watson and other services to infuse AI into your systems. DB2 on Cloud is a great way to get started with DB2. It offers 3 plans for you: Light, Standard, and Enterprise. The Light plan is free and time unlimited, meaning that you can use it in your projects without worrying about a time-limited trial period coming to an end. The plan is limited to 200 megabytes of data and 15 simultaneous connections. The Standard plan provides flexible scaling of compute capability and storage, as well as built-in 3-node high-availability clustering. And the Enterprise plan provides you with a dedicated database instance, again with flexible scaling of compute capability and storage and built-in 3-node high-availability clustering. You can deploy DB2 on cloud on the IBM Cloud Platform or on Amazon Web Services. Once running, you can access your DB2 on Cloud databases by using the CLP Plus command line interface, the DB2 on Cloud GUI console, or standard APIs such as ODBC, JDBC, and REST. You can also easily load data from Excel, CSV, and text files from Amazon S3 Object Storage using the GUI console, and you can programmatically load data from IBM Cloud Object Storage. DB2 provides high availability disaster recovery, or HADR functionality to support high availability systems. HADR replicates changes made at a primary database to multiple standby servers. If the primary database fails for any reason, hardware, software, or network issues, you can automatically promote one of the standby databases to be the primary database, redirect client applications to this new primary database, and continue to replicate to the other standby servers in the group. When the original primary database comes back online, it can either take the place of a standby server or be promoted back to the primary position. DB2 Warehouse offers massively parallel processing and data analytics for BI workloads. At times, you may need to scale the storage capabilities of your system to meet peak demand or to reduce costs when demand is low. Data in DB2 Warehouse is stored in data nodes. To scale up your storage capacity, you just need to add a node to your deployment. The partitions and their workloads are then automatically rebalanced across the new node setup. Similarly, to scale down, you just remove a node to return to your original state. In this video, you learned that DB2 is a family of products that you can use to work with and manage your data in whatever way you need. You can deploy DB2 across many platforms, both on-premises and in the cloud. Cloud Pak for Data includes DB2 and many IBM tools for data. DB2 on Cloud is a fully managed cloud-based SQL database that can run on IBM Cloud or AWS. And DB2 provides high availability, disaster recovery, and scalability functionality.
Welcome to MySQL. After watching this video, you will be able to describe MySQL and its historical background, describe the key attributes of working with MySQL, describe some MySQL storage engines, identify clustering options provided by MySQL. MySQL is an object relational database management system that plays a pivotal role in modern web development. MySQL stands out for its reliability, scalability, and ease of use. With diverse flavors and additions, it caters to different needs, even offering a clustered version designed to handle demanding workloads effectively. This versatility has contributed to MySQL's widespread adoption as an adaptable database solution across various applications and industries. Let us learn about the history of MySQL. A Swedish company, MySQL AB, initially developed MySQL, naming it after the daughter of co-founder Monty Wideness. Sun Microsystems later acquired MySQL AB, and subsequently, Oracle Corporation acquired Sun Microsystems. The MySQL logo features a dolphin named Sakila, selected from suggestions in a Name the Dolphin contest. MySQL gained popularity in the late 1990s and early 2000s because it played a crucial role in the Linux operating system, Apache web server, MySQL database, and PHP scripting language, LAMP stack. The stack was the foundation for building many of the era's popular websites. MySQL has dual licensing, offering the open-source GNU GPL and a commercial license for applications and solutions that embed MySQL. The open-source nature of GNU GPL has led to the emergence of various forks, with MariaDB being a prominent example led by some original MySQL developers. Let us now explore aspects of working with SQL. MySQL is compatible with numerous Unix versions, Microsoft Windows, and Linux. Writing client applications for MySQL is feasible with a wide range of modern programming languages. MySQL employs standard SQL syntax and introduces extensions for added functionality. For example, use of load data statement, which swiftly imports rows from a text file into a database table. MySQL works primarily with relational data, but also supports JSON. Like many other relational database management systems, RDBMS, MySQL supports multiple storage engines. The storage engine is the component that handles the SQL operations on a table and defines what feature that table can use. So, you base your choice of engine for a particular table on the expected workload and the table's requirement. Let's explore some MySQL-supported storage engines. The default MySQL storage engine is InnoDB, which supports transactions to ensure the consistency of your data, row-level locking to improve multi-user performance, clustered indexes on primary keys to increase the performance of regularly executed queries, and foreign key constraints to maintain data integrity. The engine provides a balance of high performance and reliability. MySQL also supports the MyISAM engine, which is good for workloads with mainly read operations and few updates, such as data warehouse or web applications. It uses table-level locking, which inhibits performance in a read-write environment. Another commonly used engine is the NDB engine, which supports multiple instances of MySQL servers running in a cluster. This is primarily used for applications that require high levels of availability and redundancy. MySQL supports high availability and scalability. You can use replication to create a copy of your data on one or more replicas. Changes in the source database are then simultaneously executed at the replicas. Multiple copies of the same data mean that you can share certain read loads for your data across the replica set, improving scalability. Additionally, replication boosts availability. If the source database experiences a failure, you can perform a failover to use one of the replicas instead. Let us now learn about clustering. Clustering is the practice of connecting multiple independent computing resources to work together as a unified system. MySQL provides two clustering options: InnoDB Storage Engine with Group Replication, MySQL Cluster Edition with NDB Storage Engine. The first option uses the InnoDB Storage Engine with Group Replication and enables you to work with one read-write primary server and multiple secondary servers. You can then use MySQL Router to load balance client applications across the multiple server instances, and, in the event of unplanned downtime of any of the servers, MySQL Router will reconnect client applications to an available server. Alternatively, the MySQL Cluster Edition uses the NDB Storage Engine to provide a highly available and scalable solution. Multiple MySQL server nodes access a set of data nodes, usually stored in memory. Running multiple data nodes provides redundancy and hence increased availability in the event of failure, and running multiple server nodes provides scalability. In this video, you learn that MySQL is a reliable, scalable, and widely adopted database system. MySQL is compatible with Unix, Windows, and Linux, supporting various programming languages. MySQL has dual licensing, offering GNU GPL for open source and a commercial license for embedded applications. MySQL works with relational and JSON data, supporting multiple storage engines. MySQL provides two clustering options: InnoDB with Group Replication and MySQL Cluster Edition with NDB Storage Engine.
Welcome to PostgreSQL. After watching this video, you will be able to describe PostgreSQL, explain how you can work with PostgreSQL, and describe replication functionality in PostgreSQL. PostgreSQL originates from the Postgres project at the University of California more than 30 years ago. Postgres was used for many research and production applications across a range of industries, including financial services, aviation, and medicine. In 1994, the open-source Postgres 95 was released, which included an SQL language interpreter. This was soon renamed PostgreSQL and is today generally pronounced as simply Postgres. You can use it as part of the LAPP, Linux, Apache, PostgreSQL, and PHP stack for web applications and websites. And you can also use independently developed extensions for additional functionality, such as PostGIS for geographic and spatial data handling. PostgreSQL is a free, open-source, object relational database management system. The open source part means that you can use, modify, and distribute the Postgres source code to meet your business requirements. The object part describes that, like object-oriented programming languages, it supports inheritance and overloading. You can use these techniques to simplify your design and reuse database objects. Postgres is compatible with most of today's commonly used operating systems, and its low maintenance threshold make it easy to implement in an organization. It supports many programming languages, enabling you to integrate it with your web applications, and supports ANSI SQL standards. When using Postgres, you can use all the standard relational database constructs, such as keys, transactions, views, functions, and stored procedures. And you can also use some of the NoSQL functionality, such as JSON for structured data and HStore for non-hierarchical data. Postgres supports replication for high availability. It supports two-node synchronous replication. This stores a copy of your data on a second server and applies each change you make to Node 1 at Node 2. You can then share read loads across the two servers, and if Node 1 fails, you can enable Node 2 to service all clients until Node 1 is running again. It also supports multi-node asynchronous replication for high availability and scalability. Here, one master node distributes its changes to multiple read-only replicas for scalability purposes. And again, if the read-write node fails, you can quickly replace it with one of the read-only replicas. For even greater flexibility for scaling applications, you can use commercial editions such as RDBMS PostgreSQL replication server, which provide multi-master read-write replication. This enables you to run multiple read-write databases that all replicate changes with each other. If one fails, users can easily be redirected to another instance until it is available again. Other technologies that have been added to PostgreSQL in recent releases to enhance scalability and working with larger datasets include partitioning, which enables you to split a large table into multiple smaller sections, or partitions to improve query performance, and sharding, which enables you to store horizontal partitions across multiple remote servers. In this video, you learned that PostgreSQL is an open-source object relational database. It supports a range of languages for client application development. It supports relational, structured, and non-structured data. And it supports replication and partitioning for high availability and scalability. Welcome to Types of SQL Statements. At the end of this video, you will be able to distinguish between data definition language statements and data manipulation language statements. SQL statements are used for interacting with entities, that is, tables, attributes, that is, columns, and their tuples, or rows with data values, in relational databases. SQL statements fall into two different categories: data definition language statements and data manipulation language statements. Data definition language, or DDL statements, are used to define, change, or drop database objects such as tables. Common DDL statement types include create, alter, truncate, and drop. Create, which is used for creating tables and defining its columns. Alter is used for altering tables, including adding and dropping columns and modifying their data types. Truncate is used for deleting data in a table, but not the table itself. Drop is used for deleting tables. Data manipulation language, or DML statements, are used to read and modify data in tables. These are also sometimes referred to as CRUD operations, that is, create, read, update, and delete rows in a table. Common DML statement types include insert, select, update, and delete. Insert is used for inserting a row or several rows of data into a table. Select reads or selects row or rows from a table. Update edits row or rows in a table, and delete removes a row or rows of data from a table. Now you know that DDL, or data definition language statements, are used for defining or changing objects in a database, such as tables. And DML, or data manipulation language statements, are used for manipulating or working with data in tables. Thanks for watching this video.
Welcome to Create Table Statement. After watching this video, you will be able to explain how the entity name and attributes are used to create a relational database table. Now let's look at the most common DDL statement, create. The syntax of the create table is shown here. Initiate the process by using create table, followed by specifying the desired name for the table you wish to create. Then, enclose the rest of the statement inside a pair of parentheses or round brackets. Each row inside the parentheses specifies the name of a column, followed by its data type, and possibly some additional optional values that we will see later. Separate each attribute or column definition with a comma. For example, if we want to create a table for provinces in Canada, you would specify create table provinces parentheses ID char 2 primary key not null comma name varchar 24 parentheses. In this example, the data types used are char, which is a character string of a fixed length, in this case 2, and varchar, which is a character string of a variable length. In this case, this variable character field can be up to 24 characters long. Issuing this statement would create a table in the database with 2 columns. The first column ID for storing the abbreviated 2-letter province shortcodes such as AB, BC, and so on. The second column is called name for storing the full name of the province, such as Alberta, British Columbia, and so on. Now, let's look at a more elaborate example based on the library database. The database includes several entities, such as author, book, borrower, and so on. Let's start by creating the table for the author entity. The table is named author, and its columns, such as author ID, first name, last name, and so on, represent its attributes. Within this table, we will designate the author ID attribute as the primary key to ensure the absence of duplicate values. Recall that the primary key of a relational table uniquely identifies each tuple or row in a table. To create the author table, issue the following command. Create table author, parenthesis, author ID char2, primary key not null, last name varchar 15 not null, first name varchar 15 not null, email varchar 40, city varchar 15, country char 2, parentheses. Note that the author ID is the primary key. This constraint prevents duplicate values in the table. Also, note that the last name and first name have the constraint not null. This ensures that the fields cannot contain a null value since an author must have a name. In this video, you learn that create is a DDL statement for creating entities or tables in a database. The create table statement encompasses the definition of column attributes within the table, comprising column names, data types, optional values like the primary key constraint if needed. Welcome to Creating Tables. After watching this video, you will be able to identify key considerations for creating tables, outline the steps to create a table in DB2 on cloud, describe the process of modifying a table structure after its creation. Creating a table in a relational database requires careful consideration and information gathering. Here are a few key considerations. Firstly, choose the location for table creation, considering the presence of schemas in many relational databases. Schemas offer a means to organize database objects logically. Next, collect all necessary details for table creation, including a name for the table and names and data types for each column. You should also consider whether a column can contain duplicate values or if a column will allow null values. Utilize the Entity Relationship Diagram, ERD, created during database design as a helpful reference. Lastly, confirm that you have a complete set of information needed for table creation to avoid issues later in the process. There are several methods for creating tables in a relational database. Here are some common methods. Using visual interface or UI tools, using SQL statements, using APIs. Let us learn more about these methods. Many relational databases provide a visual interface or UI tools that allow users to create and modify tables using a graphical representation. It is often suitable for small-scale or occasional tasks and is user-friendly for those not familiar with SQL. A few examples include DB2 on Cloud Console, MySQL PHP MyAdmin, and PostgreSQL PGA Admin. Another common method involves using SQL statements, specifically the create table statement. Include the statement in a script file to help you automate the creation process when you are creating multiple tables. Some databases also provide administrative application programming interfaces, APIs, that allow for programmatic creation and management of tables. These APIs help interact with the database at a higher level, providing more control and automation options. For example, MongoDB with PyMongo, Python driver. The DB2 on Cloud Console is the user interface provided by IBM to interact with and manage DB2 databases in the cloud. Creating a table using the DB2 on the Cloud Console involves a step-by-step process. Here's a breakdown of the key steps: choosing a schema, creating a new table, and configuring table columns and data types. Let us explore the steps in detail. The first step is to select a schema to hold the table. The default schema in DB2 is often the username. In the provided example, the username is schema name. Each user will have a unique username in their DB2 database. You can create new schemas to hold your tables, views, and other database objects. After choosing the schema, proceed to create a new table. Provide a name for the table. For instance, the example names it Employee Details. The fully qualified name for this table, considering the selected schema name, would be schemaname.employeedetails. By default, the new table has a single column. You can rename this column to suit your needs. Set the data type for the column by choosing from the available options. Use the Add Column option to continue adding columns until you define the entire table structure. Specify data types, decide on null value acceptance, and provide length and scale as needed. Lastly, click the Create button to finalize the table creation. You can also alter a table structure after its creation, which involves modifying the existing table. You can perform the following actions after creating the table. You can drop or delete the table. You can also generate SQL code to perform actions such as select, insert, update, and delete. Next, you can modify the table by adding new columns, setting constraints, or altering its structure. Lastly, you can explore the database objects that the table relies on. In this video, you learn that, in creating tables, key considerations involve choosing the location, collecting details, and referencing the ERD. Methods for creating tables include using visual interfaces, SQL statements, and administrative APIs. The DB2 on Cloud Console is an example of a visual interface for managing DB2 databases. Steps for creating a table in DB2 include selecting a schema, creating the table, and configuring columns. Post-creation actions include dropping the table, generating SQL code, modifying the structure, and exploring dependencies. Welcome to Alter, Drop, and Truncate Tables. After watching this video, you will be able to describe the alter table, drop table, and truncate statements, explain the syntax, use the statements in queries. You use the alter table statements to add or remove columns from a table, to modify the data type of columns, to add or remove keys, and to add or remove constraints. The syntax of the alter table statement is shown here. You start with alter table, followed by the name of the table that you want to alter. Differently to the create table statement, though, you do not use parentheses to enclose the parameters for the alter table statement. Each row in the alter table statement specifies one change that you want to make to the table. For example, to add a telephone number column to the author table in the library database to store the author's telephone number, use the following statement: alter table, author, add column, telephone, _number, bigint. In this example, the data type for the column is bigint, which can hold a number up to 19 digits long. You also use the alter table statement to modify the data type of a column. To do this, use the alter column clause specifying the new data type for the column. For example, using a numeric data type for telephone number means that you cannot include parentheses, plus signs, or dashes as part of the number. You can change the column to use the car data type to overcome this. This code shows how to alter the author table. Alter table author, alter column, telephone _number, set data type car, 20. Altering the data type of a column containing existing data can cause problems, though, if the existing data is not compatible with the new data type. For example, changing a column from the car character type to a numeric data type will not work if the column already contains non-numeric data. If you try to do this, you will see an error message in the notification log and the statement will not run. If your spec changes and you no longer need this extra column, you can again use the alter table statement, this time with the drop column clause, to remove the column as shown. Alter table author, drop column, telephone _ number. Similar to using drop column to delete a column from a table, you use the drop table statement to delete a table from a database. When you delete a table that holds data, the data will be automatically removed along with the table by default. The syntax for the drop table statement is drop table, table _ name. So, you use this statement, drop table, author, to remove the table from the database. Sometimes, you might want to just delete the data in a table rather than deleting the table itself. While you can use the delete statement without a where clause to do this, it is generally quicker and more efficient to truncate the table instead. You use the truncate table statement to delete all of the rows in a table. The syntax of the statement is truncate table, table _ name, immediate. Immediate indicates an immediate processing of the statement and emphasizes that the action cannot be reversed. So, to truncate the author table, you use this statement, truncate table, author, immediate. In this video, you learn that the alter table statement changes the structure of an existing table, for example, to add, modify, or drop columns. The drop table statement deletes an existing table, and the truncate table statement deletes all rows of data in a table. Welcome to Data Movement Utilities. After watching this video, you will be able to identify reasons for moving data in and out of databases, compare methods for data movement, including backup, restore, import, and export, identify various file formats for importing and exporting data, evaluating their suitability, recognize the efficiency of data movement operations using different database utilities. Data engineers and database administrators often need to move data into and out of an existing database. There are multiple reasons for this action. These include populating the database and its objects, like tables, creating a duplicate database for development and testing needs, creating a snapshot of the state of the database for disaster recovery, generating a new table using data from external sources or files, adding data into one or more existing tables. Most databases support different ways to move data in and out of the database using multiple file formats. Each database has its tools and utilities for data movement, but for this lesson, we will classify them into 3 categories: backup and restore, import and export, and load. Let's explore each of these. One method for moving data between databases is to perform backup and restore. The backup operation creates a file, or a set of files, that encapsulates all the database objects and their data. The restore operation creates an exact copy of the original database from the backup files. Backup and restore operations preserve all objects in the database, including schemas, tables, views, user-defined data types, functions, stored procedures, table constraints, triggers, security settings, relationships between objects, and the data in all the tables. Backups are essential to preserve copies of the production database for disaster recovery purposes. You can also perform backup and restore operations to create additional database copies for development and test purposes. The important operation reads data from a file and performs a series of insert statements against the target table. The export operation retrieves data from the designated table and stores it in a chosen file. Users can perform import and export operations using multiple interfaces. Most databases provide at least a command line utility. Management APIs include support for import and export. The graphical or web administration tools include a visual interface for these operations. And there are also third-party tools that enable users to perform these operations with different RDBMSs. Most databases support multiple file formats for importing and exporting data. The most commonly used formats are DEL. Delimited ASCII allows data exchange among various database and file managers. utilizing special character delimiters to separate column values. It illustrates a common approach to storing data, with comma-separated variable files being a well-known example. ASC, non-delimited ASCII, imports data from applications generating flat text files with aligned columns. PC/IXF. The PC version of the Integration Exchange format, IXF, represents the preferred method for data exchange within the Database Manager. PC/IXF presents a structured description of a database table containing an external representation of the internal table. JSON. With the popularity of JSON and REST web services, some databases and third-party tools have also started to support importing and exporting data to and from JSON files. Let's explore some examples of import and export operations from different interfaces. In DB2, the command line import and export utilities allows you to type the file names, formats, table names, and message files for importing and exporting data. Note that the export utility in DB2 allows you to specify an SQL query and export a subset of the data in a specified table. The DB2 for Cloud Web Console includes a visual interface that allows you to export the results of any table or query and save it as a CSV file. In your schema, select the table you want to export, then click View Data, select the Export button, then click Export to CSV. You can specify a name and location to save the CSV file. As an alternative to the import utility, some databases provide load utilities. The load utility outperforms the import utility by directly formatting pages into the database rather than running SQL insert statements, like the import process. However, it does not perform referential or table constraint checking, so you may prefer the import utility if you need those extra checks. The load utilities may also bypass database logging, which also helps with higher performance. While import may work well for smaller tables, the load utilities are preferred for large volumes of data. You can activate the DB2 import utility from the command line, call its API through an application, or use visual database management tools. In this video, you learn that data movement is essential for the initial population of databases and tables. Backup and restore utilities actively create and recover copies of entire databases. The import utility facilitates data insertion into a specific table from various formats. The export utility allows preserving data from a specific table in various formats, like CSV. Load utilities provide high-performance data insertion into specified tables. Welcome to Loading Data. After watching this video, you will be able to explain when to use load data functionality, list the types of data sources you can load data from, describe the 4 steps in the load data process in the DB2 Web Console. Using SQL statements such as insert to add data into tables can work well for a few rows or when you are developing and testing your database systems. However, it's often not practical to use this method to load hundreds or thousands of rows of data. Instead, most relational database management systems, or RDBMS, provide a method of directly loading large amounts of data into tables in a quick, efficient, and scalable manner. Your data might originate from a range of different sources in a variety of formats. For example, you might want to populate your table with information exported from another database in delimited text files or object data output from a bespoke application. In the DB2 Web Console, you can use the Load Data utility to load data stored in delimited text files on your local computer, in S3 Object Storage, that is, the storage service from Amazon Web Services, or in Cloud Object Storage, that is, the cloud storage service from IBM. So let's look at an example of how to load data into a table from a CSV file using the DB2 Web Console. To begin loading data, in the Web Console, open the 3-bar menu, and in the Load section, click Load Data. You then follow a series of 4 steps to define how to load your source data into your target tables. First, identify the type and location of your source data. Then select the target for the data. Next, define any configurable aspects of the data. And then finally, confirm everything before starting the load process. On the source page, select the location of the existing data and enter any authentication information which that storage type requires. For example, for data in IBM Cloud Object Storage, you provide the COS authentication endpoint, access key, and secret access key. Whereas for a locally stored CSV file, you simply identify the file to upload. On the target page, select the target schema and table for data location. You can also specify whether to append the new data to the end of the table or overwrite the existing data with the new data. Note that if you use the overwrite option, even if your load fails, you will still lose all of the existing data in that table. Alternatively, you can click New Table to load the data into an entirely new table using the format of the new data to define the data types for the columns. On the Define page, you define the character encoding and delimiter for the text file, whether there are column headings in the first row, and what time and date formats to use. And on the Finalize page, you can review all the settings before beginning to load the data. When the load completes, the console displays the status of the process and also shows any errors or warnings that the load process has raised. In this video, you learn that loading data is quicker, more efficient, and more scalable than using multiple insert statements. You can load data from a variety of data sources, including delimited text files and cloud object storage. The Load Data utility is a simple-to-use interface in the DB2 web console. Welcome to Database Objects and Hierarchy, including schemas. After watching this video, you will be able to describe the hierarchical structure of database objects, explain the significance of database instances, define relational database, describe schema functionality and usage. Relational Database Management Systems, RDBMSs, contain many objects that database engineers and database administrators must organize. Storing tables, constraints, indexes, and other database objects in a hierarchical structure allows database administrators to manage security, maintenance, and accessibility. This hierarchy gives you an overview of how RDBMSs are structured, although slight variations may occur between products. Most RDBMSs begin with an instance, a single way of organizing the database and everything it contains. Many RDBMSs permit more than one database within a single instance. You will generally find at least one schema at some level in the hierarchy. A schema is a logical grouping of objects within a database. Schemas define how database objects are named and prevent ambiguous references. Some RDBMSs consider the schema a parent object of a database, and others consider it a database object. There are database objects within a schema, including tables, constraints, and indexes. An instance is a logical boundary for a database, or set of databases where you organize database objects and set configuration parameters. Every database within an instance is assigned a unique name, has its own set of system catalog tables, which keep track of the objects within the database, and has its own configuration files. You have the option to generate multiple instances on a single physical server, ensuring a distinct database server environment for each instance. The databases and other objects within one instance are isolated from those in any other instance. It is possible to establish multiple instances on a single physical server, thereby creating distinct database server environments for each instance. Not all RDBMSs use the concept of instances, often managing database configuration information in a special database instead. In cloud-based RDBMSs, the term instance means a specific running copy of a service. A relational database comprises objects designed for the storage, management, and retrieval of data. These objects include tables, views, indexes, functions, triggers, and packages. Database objects can be either defined by the system, built-in objects, or defined by the user, user-defined objects. In a relational database, database engineers establish relationships between tables to reduce redundant data and improve data integrity. A distributed relational database shares tables and other objects across different but interconnected computer systems. A schema is a specialized database object that provides a way to group other database objects logically. A schema has the capability to include tables, views, nicknames, triggers, functions, packages, and various other objects. When you create a database object, you can assign it to a schema. If you want to assign the object to a specific schema, you can explicitly include the schema name. If you don't include the schema name, the object is implicitly assigned to the current schema. In most RDBMSs, the default schema is the user schema for the currently logged on user. A schema also provides a naming context. Using the schema name as a name qualifier enables you to distinguish between objects with the same name in different schemas. For example, the schema names internal and external make it easy to distinguish two different sales tables, internal sales in the internal schema and external sales in the external schema. Thus, schemas enable multiple applications to store data in a single database without encountering namespace conflicts. Many RDBMSs use a specialized schema to hold configuration information and metadata about a particular database. For example, tables in a system schema can store lists of database users and their access permissions, information about the indexes on tables, details of any database partitions that exist, and user-defined data types. A partitioned relational database is one where data is distributed and managed across multiple database partitions within the relational database system. You can partition tables that need to contain large quantities of data into multiple logical partitions, with each partition containing a subset of the overall data. Database partitioning is used in scenarios that involve large volumes of data, such as data warehousing and data analysis for business intelligence. Database objects encompass items present within the database. The process of database design includes defining database objects and their relationships with each other. In most RDBMSs, you can create objects such as tables. These are logical structures consisting of rows and columns that store data. Constraints. Within any business, data is often subject to certain restrictions or rules. For example, it is imperative for an employee number to be distinct or unique. Constraints provide a way to enforce such rules. Indexes. An index is a set of pointers used to improve performance and ensure the uniqueness of the data. Views. A view provides a different way of representing the data in one or more tables. It's important to note that a view is not an actual table and does not demand permanent storage. Aliases. An alias serves as an alternative name for an object, such as a table. It can be used to provide a shorter, simpler name to reference an object. You can create and manage database objects through graphical database management tools, scripting, or accessing the database through an API. If you are using SQL to create or manage the object, you will use data definition language statements like create or alter. In this video, you learn that an instance is a logical and configuration boundary. A relational database is a set of related objects used to store, manage, and access data. A schema provides a way to logically group views, tables, triggers, nicknames, packages, functions, and other database objects. User schemas contain database objects like tables, views, functions. System schemas contain configuration and metadata for the database. You can split large tables across multiple partitions to enhance performance. Data objects encompass items present within the database. Welcome to Primary Keys and Foreign Keys. After watching this video, you will be able to describe primary and foreign keys, outline the steps to create primary and foreign keys. You can use a primary key to uniquely identify every row in a table. In some tables, the choice of the primary key is easy because it is a naturally occurring unique attribute of an entity. For example, the book ID of a book or the employee ID number of a staff member. If your table doesn't have an existing unique attribute, you can add a column to the table to serve as the primary key. Or, if a combination of the two attributes uniquely identifies each row, you can create a primary key across the two columns. For example, where employees have a unique identifier within their work site, you can use the combination of their site ID and employee ID. Note that each table can only have one primary key. You can create a primary key when you create the table by using the primary key clause and the create table statement. in the parentheses for the primary key clause, state the name of the column or columns that will be the primary key. Alternatively, you can create a primary key on the existing table by using the Add Primary Key clause of the Alter Table statement, and again, in the parentheses, state the name of the column or columns that will be the primary key. You use primary and foreign keys to define the relationships between your tables. A foreign key is a table column that holds information identical to the primary key in another table. For example, the copy table might list all books that the library owns. Therefore, the book ID of a copy of an individual book must exist in the book table as a valid book. When the library owns multiple copies of a popular book, the book ID of that particular book will appear multiple times in the copy table. You can also specify that whenever you add a row to the copy table, the book ID you use must already exist in the book table. Similarly to primary keys, you can create a foreign key when you create the table by using the constraint name, foreign key clause of the create table statement. In the parentheses for the foreign key clause, state the name of the column or columns that will be the foreign key, and then reference the table and primary key column that the foreign key links to. You can also use the rule clause to define what action to take if a row in the parent table, the table with the primary key, is updated or deleted. For updates and deletes, you can specify to take no action, in which case the update or delete option on the parent table may fail. For deletions, you can also specify to cascade the delete, that is, to delete the related child row in the dependent table or to set the values in the foreign key column of the child table to null. Alternatively, you can create a primary key on an existing table by using the Add Primary Key clause of the Alter Table statement, and again, in the parentheses, state the name of the column or columns that will be the primary key. Note to use a comma to separate the column names when using multiple columns for a primary key. In this video, you learn that you can use primary keys to enforce the uniqueness of rows in a table. Foreign keys are columns in a table which contain the same information as the primary key in another table. You can use primary and foreign keys to create relationships between tables. Welcome to Overview of Indexes. After watching this video, you will be able to describe an index and its uses, explain the improvement of database performance through indexing, describe the advantages and disadvantages of using indexes. Imagine you have a library with a collection of books. If you want to find a specific book, you could go through each shelf individually until you find it. However, this approach can be quite time-consuming and inefficient. A better way to locate the book would be to use the library's catalog. The catalog is an index of all the books in the library, and it lists each book by its title, author, and other relevant information. When you use the catalog to find a book, you navigate through the index to locate its entry. Indexing a table in a database works similarly. An index is a data structure that allows you to find specific rows in a table based on certain criteria quickly. For example, if you have a customer data table, you could create an index in the customer's name column. Indexing would allow you to find all the table rows belonging to a specific customer quickly. Here are some real-world examples of how databases use indexing. Some of these examples include online shopping websites, airline reservation systems, and bank ATMs. When you search for a product on an online shopping website, the website uses indexes to locate products that align with your search criteria efficiently. When you search for a flight on an airline website, the website uses indexes to find the flights that meet your criteria quickly. Lastly, when you withdraw money from an ATM, the ATM uses indexes to retrieve your account information quickly. Let us now explore how indexing is essential for optimizing database performance. Indexes can significantly improve the performance of database queries. They allow the database to quickly find the relevant rows to the query without scanning the entire table. Usually, when you add data to a table, it is added to the end of the table. However, this action has no guarantee or inherent order to the data. So, when you select a particular row from that table, the processor must check each row until it finds the one you want. On a large table, it can significantly slow down the process of locating a specific row. Also, when you select multiple rows, the result may lack a specific order unless you specify a sort order in your select statement. As you might want to return the rows in a particular order or select a subset of sequential rows, you can create an index on a table to locate the row or set of rows that you need quickly. Let us now explore how an index works. An index works by storing pointers to each row in the table so that when you request a particular row, the SQL processor can use the index to locate the row quickly. It is similar to how you use the index in a book to find a particular section quickly. The unique key dictates the order of the index on which values rely. By default, when you create a primary key on a table, the system automatically generates an index on that key. However, you can also create your indexes on regularly searched columns. Use the create index statement to define the index, specifying the index name, its uniqueness, and the table and column on which to base it. Indexes provide the database user with many benefits. These include improved performance of select, reduced need to sort data, and guaranteed uniqueness of rows. Improved performance of select queries when searching on an indexed column. Because the index offers a quick route to locate rows matching the search term, it returns results faster than when it needs to check every row in the table. Reduced need to sort data. If you constantly need rows in a specific order, employing an index can eliminate the necessity to sort the rows after their retrieval. Guaranteed uniqueness of rows. If you use the unique clause when you create the index, you ensure that updates and insertions won't result in duplicate entries in that column. There are, however, a few disadvantages of indexes as well. These include use of disk space. Each index you create uses disk space in the same way that adding indexes increases the number of pages in a book. Decreased performance of insert, update, and delete queries. Because the rows in an index table are sorted according to the index, adding or removing rows can take longer than a non-indexed table. In this video, you learn that an index is a data structure that allows you to quickly find specific rows in a table based on certain criteria. Indexing is an essential tool for optimizing database performance. An index works by storing pointers to each row in the table so that when you request a particular row, the SQL processor can use the index to locate the row quickly. You should create an index only when you stand to gain more from the advantages than you might lose from the disadvantages. Welcome to normalization. After watching this video, you will be able to explain the purpose of normalization, describe the first normal form, describe the second normal form, describe the third normal form. When you keep records of data, such as books in a bookshop, you will inevitably have some inconsistencies and duplicate information. Such duplication can cause extra work and inconsistencies if the data is updated, because you must change it in more than one place. Normalization is the process of organizing your data to reduce redundant data, often by dividing larger tables into multiple relatable tables. Normalization helps speed up transactions because you perform updates, additions, and deletes only once on a normalized database. It also improves data integrity because it reduces the chance of a change being made in one place but not in another. As you begin the normalization process, it's important to recognize that you focus on normalizing each table until you reach the required normal form level. Normalization usually results in creating more tables, and once all the tables are normalized, you will have a normalized database. There are several forms of normalization, and most data engineers will need to be familiar with the first normal form, second normal form, and third normal form. For a table to be in the first normal form, each row must be unique, and each cell must contain only a single value. First normal form is also called 1NF. Let's look at how you would normalize a simple table. In this example, the book table contains some basic information about books, including titles, formats, and authors. To adhere to the requirements of the first normal form, it is essential that each cell contains a singular value rather than a list. In this example, you can observe that all variations of a book's format are recorded within the same cell. To normalize this table, You can add an extra row and split the two formats of patterns and software into their own row. So now you have a row for the paperback version and a row for the hardback version. Each cell in the table now has only one entry, and so the table is in the first normal form. To be in the second normal form, the database must already be in first normal form, involves ensuring that every row in the table is unique and that each cell contains only a single value. Second normal form specifies that you should separate groups of values that apply to multiple rows by creating new tables. Second normal form is also referred to as 2NF. For clarity, this example shows just a subset of the data in the book table. Book 401 comes in both paperback and hardback format, so in its current form, it must be listed twice, once for each format. In this case, the format column contains values that apply to both rows that reference Book 401, so there is some data duplication. To meet the requirements for the second normal form and achieve just one row for Book 401, you can split the book table so that the format information for the book is separated from unrelated information such as title and author. Each resulting table is in 1NF. To maintain a relationship between the two tables, identify a primary key for one table that will be used as a foreign key in the other. In this example, the book ID is unique to each book, so you can make that the primary key in the book table and include it as a foreign key in the format table. Now, you can use it to link between the two tables to find the different formats of each of the unique books. The database must already be in the first and second normal forms to meet the requirements for the third normal form. Next, you must eliminate any columns that do not depend on the key. Third normal form is also referred to as 3NF. Let's consider some additional data about books, the publisher, and where the book ships from. Each publisher ships books from warehouses in their own location, so where the book ships from depends on the publisher, not the book ID. Therefore, the book table is not in 3NF because the ships from data does not depend on the primary key. To fulfill the criteria of the third normal form, 3NF, it is necessary to segregate the publisher and ships details into a dedicated publishers table. Both tables are now in third normal form, which is as far as most relational databases go. There are also higher normal forms, such as Boyce Codd normal form or BCNF, which is an extension to the third normal form, as well as fourth and fifth normal forms, which may be needed for specific scenarios. In transactional systems, OLTP, where data is both read and written frequently, you typically normalize the data to 3NF. OLTP systems need to process and store transactions, as well as query transactional data, and normalizing the data to 3NF helps the database to process and store individual transactions efficiently. In analytical OLAP systems, where users primarily read data, databases prioritize read performance over write integrity. Hence, the data may have undergone some denormalization to a lower normal form before being loaded into the analytical system, such as a data warehouse. In data warehousing, data engineers focus on performance, which can benefit from having fewer tables to process. In this video, you learn that normalization reduces redundancy and increases the consistency of data. In the first normal form, or 1NF, each row must be unique, and each cell must contain only a single item. In the second normal form, or 2NF, you must create separate tables for sets of values that apply to multiple records. In third normal form, or 3NF, eliminate any columns that do not depend on the key. Welcome to Relational Model Constraints. After watching this video, you will be able to list the different types of relational model constraints, describe the different types of relational model constraints. In a business, a data relational model needs to adhere to certain restrictions or rules. In a relational data model, data integrity can be implemented using integrity rules or constraints. The following 6 constraints are defined in a relational database model: entity integrity constraint, referential integrity constraint, semantic integrity constraint, domain constraint, null constraint, and check constraint. To identify each tuple in a relation, the relation must have a primary key. The primary key is a unique value that identifies each tuple or row in a table. This is the entity integrity constraint. The terms primary key constraint or unique constraint are also used. This constraint prevents duplicate values in a table. To implement these constraints, indexes are used. According to the entity integrity constraint, no attribute that is a part of the primary key of a relation should have null values. The value null indicates that the value is unknown. In the entity integrity constraint, the primary key cannot have an unknown value. For example, in the relation author, author ID is the primary key. The primary key identifies each tuple in the relation. The author ID A1 points to author Raul Chong from Toronto. If you replace the value A1 with null, you can still identify the author as Raul Chong. However, if you also replace author ID A4 with null, now you do not know which null value identifies which tuple. With the entity integrity constraint, no attribute participating in the primary key is allowed to accept null values. Relationships between tables are defined by the referential integrity constraint. This constraint endorses the relationships between tables. The validity of the data is enforced using a combination of primary keys and foreign keys. As mentioned previously, for a book to exist, it has to be written by at least one author. The correctness of the data in a table is enforced by the semantic integrity constraint. For example, in the relation author, if the attribute or column city contains a garbage value instead of Toronto, the garbage value does not have any meaning. The semantic integrity constraint is related to the correctness of the data. A domain constraint checks for valid values for a given attribute. For example, in the relation author, the attribute country must contain a two-letter country code, such as CA for Canada or IN for India. If a number value of 34 is entered for the country attribute instead of a two-letter country code, the value 34 does not have any meaning. As observed earlier, the entity integrity constraint states that no attribute that is part of the primary key should accept null values. The null constraint ensures that attribute values should not be null. For example, in the relation author, if either last name or first name contains a null value, it could be difficult to identify the correct author. In this example, first name and last name attribute values cannot be null. An author must have a name. The check constraint enforces domain integrity by limiting the values that are accepted by an attribute. In the relation book, the attribute year is the year in which a particular book is published. If this was still the year 2010, it would not be meaningful to have a year greater than the current year. The check constraint would enforce the domain integrity by limiting the values that are accepted by the attribute year. In this video, you learn that entity integrity constraint checks that the value in the primary key is a unique value which identifies each tuple or row. Referential integrity constraint specifies the relationships which exist between tables. Semantic integrity constraint enforces the correctness of the meaning of the data. Domain constraint ensures that valid values are entered for a given attribute. Null constraint ensures that attribute values should not be null. Check constraint limits the values that are accepted by an attribute. Welcome to Getting Started with MySQL. After watching this video, you will be able to define MySQL along with its deployment options, explain the various applications of MySQL, identify some popular MySQL administration tools and their applications. MySQL is an open-source relational database management system, RDBMS, that enables the creation, management, and interaction with databases. MariaDB is a fork of the MySQL database by some of the original developers of MySQL. MySQL is available for usage in a variety of ways to suit your needs. You can download and install the free Community Edition under a GNU General Public License and embed this in your applications. Alternatively, commercial editions like Standard, Enterprise, and Cluster versions with added features are available for purchase. MySQL is also accessible in the cloud, allowing self-management in virtual machines or containers. Managed services like IBM Cloud, Amazon RDS, Azure Database, and Google Cloud SQL offer convenient options for MySQL deployment. MySQL is popular for storing and retrieving data in diverse computing environments. Here are a few practical applications of MySQL. Large-scale websites like Facebook, YouTube, and Twitter favor MySQL for its scalability, performance, and reliability. It serves as a preferred choice for e-commerce platforms such as Shopify, Magento, and WooCommerce, handling substantial product data, customer information, and transactions. MySQL's affordability, user-friendly interface, and diverse features make it popular among small and medium-sized businesses, supporting internal databases, customer relationship management, CRM systems, and accounting software. Let us now explore various tools available to facilitate database management. These include MySQL Command Line Interface, MySQL CLI, MySQL Admin Command Line Program for RDBMS administration, specialized MySQL utilities for specific tasks, MySQL Workbench desktop application for Windows, Linux, and Mac OS, third-party web interface, PHP-MyAdmin, for efficient MySQL database management. Let us discuss these tools in detail. The MySQL CLI facilitates interaction with the MySQL server and data through commands, either interactively or from a specified text file. The Show Databases command is demonstrated in a screenshot and lists available databases. In batch mode, you can specify output messages for later use. Here are a few applications of MySQL CLI. Database administrators rely on MySQL CLI for direct server interaction, permissions management, and database monitoring. Developers favor MySQL CLI for streamlined tasks like database creation, modification, and scripting. System administrators use MySQL CLI for server configuration, performance tuning, and troubleshooting, ensuring efficient database management at the system level. Let us now learn about MySQL Workbench. MySQL Workbench seamlessly integrates SQL development, administration, and database design within a unified environment for MySQL. The administration page offers insights into connection details and server features and allows tasks like data import/export. Server logs and performance reports are also accessible. On the Schemas page, users navigate database objects, manage data, and access help documentation directly. Let us now explore how the Visual Database Design tool caters to diverse roles. Database developers and designers benefit from its extensive features for MySQL database design and management. Database administrators find value in tasks like performance monitoring, schema management, and user administration. Data analysts and scientists leverage MySQL Workbench's visual interface for exploring and analyzing MySQL data. MySQL Workbench is also popular for software development companies because it provides a comprehensive set of tools for designing, developing, and deploying MySQL databases. PHP-MyAdmin serves as a graphical user interface, GUI, for MySQL database interaction. Upon connecting to the server, users access server information and system databases. With PHP-MyAdmin, users create custom databases, utilizing various tabs for interactions. Let us learn about its application. This web-based tool is popular among web hosting providers for its accessibility via any browser. Individual website owners, especially those with limited technical expertise, commonly rely on PHP-MyAdmin for MySQL database management. Moreover, various content management systems, CMS, like WordPress and Drupal, integrate PHP-MyAdmin as a built-in tool, extending its usability to CMS users for efficient MySQL database management. MySQL Workbench and PHP-MyAdmin are distinct tools catering to diverse needs. While MySQL Workbench is a desktop application, PHP-MyAdmin operates as a web-based tool. MySQL Workbench is available in both commercial and open source versions, whereas PHPMyAdmin is available for free and as open source software. MySQL Workbench provides a comprehensive toolkit for designing, developing, and deploying MySQL databases. On the other hand, PHPMyAdmin is a simple and easy-to-use tool for managing MySQL databases. MySQL Workbench caters to software development companies, database administrators, and data analysts, whereas PHPMyAdmin is suitable for web hosting companies, small businesses, and individual users. In this video, you learn that MySQL is an open-source RDBMS known for scalability and reliability. MySQL is available in various forms, including a free community edition, commercial version, and cloud deployment. MySQL CLI Workbench and PHPMyAdmin are key administration tools for database management. MySQL CLI facilitates interaction with the MySQL server and data through commands. MySQL Workbench integrates SQL development, administration, and design. PHPMyAdmin is a web-based GUI favored by web hosting providers and individual website owners.
Welcome to creating databases and tables in MySQL. After watching this video, you will be able to create a database and table at the command line, create a database using PHPMyAdmin, create a table, define columns, and edit the table definition. As with many RDBMS, you can create databases and tables in MySQL by using a command line interface, a graphical user interface, or API calls. In this video, you will see how to perform these tasks using the command line and the PHPMyAdmin user interface. You will see how to create the database, then the table, and then how to define and edit the columns in that table. You can issue commands at the MySQL command line to create database objects. Use the Create Database command to create the database and create table for tables, specifying column names and data types. You can use the Describe command to show the structure of the newly created table. Alternatively, you can use PHPMyAdmin to create the same database and table. PHPMyAdmin is a popular visual tool with a web interface for working with MySQL. To create the database, in the tree view in the left-hand pane, click New. On the Databases tab, enter the name for the new database. Optionally, select the encoding for the data, and then click Create. This creates the database, which now shows in the database tree view on the left-hand side of the window and opens the Create Table tab. To create a table, enter the name of the table, in this case, employee_details, select the number of columns for the table, 4, and then click Go. In the next step, you define the columns for your table. Enter the name, select the data type, enter a length if relevant to that data type, and then click Save. You're then shown a summary of the structure of the new table in your database. Here, you can edit columns, drop columns, move them, or normalize the table. You can also add more columns if required. In this video, you learned that you can use a command line interface, a graphical user interface, or API calls to create databases and tables in MySQL. PHPMyAdmin provides an easy-to-use interface to create databases, tables, and columns. And you can add and modify columns after you create a table. Welcome to populating MySQL databases and tables. After watching this video, you will be able to describe MySQL backup and restore functionality, explain how to load small and large amounts of data into MySQL, and describe how to export MySQL data to a CSV file. As a data engineer or database administrator, you will often need to populate databases and tables. One method of doing this is to back up an existing database containing your data and restore it to your new destination. You can use MySQL dump to back up a database to a .sql file containing all of the statements needed to recreate the contents of the database. The simplest use of this is shown here. The -u parameter specifies the username of root. Employees is the name of the database, and employee backup.sql is the name of the file in which to create the backup. If you want to just back up specific tables, you can list their names after the name of the database. And to restore a backed up file, you can use MySQL in a similar fashion. This runs all the SQL statements in the backup file to recreate the objects and restore the data in the destination database. Note that the greater than sign signifies output to the .sql file or backup, and the less than sign signifies input to the database or restore. If you're already at the MySQL command prompt, you can restore a dump file by using the source command with the name of the dump file. This method can also be used to execute SQL scripts from file. You can also back up databases using phpMyAdmin. Select a database in the tree view. Then, on the Export tab, click Go. By default, this quick export method generates an SQL file that contains all the script necessary to completely recreate the contents of your database. You can then use the Import tab to restore this database to this or another instance of MySQL. Select your destination database, locate the backup file, and then click Go. Again, this runs all the SQL statements in the backup file to recreate the objects and restore the data in the destination database. Alternatively, if you only want to populate a small number of rows in an individual table, instead of populating an entire database, you can use the phpMyAdmin tool to manually enter rows or run SQL insert statements. To manually enter rows in phpMyAdmin, on the Insert tab, enter the data, then click Go. By default, you can enter 2 rows at a time, but you can increase or decrease this as required. And after you have entered data into a table, you can view that data on the Browse tab. Manually entering rows and running individual SQL statements is fine for small amounts of data, but if you're loading a large number of rows, you will find the import functionality is easier and quicker to use. You can use the MySQL load data in file statement to import the contents of a CSV file into an existing MySQL table, or you can use the MySQL import utility passing the name of the database that the table resides in and the name of the CSV file. The table name is inferred from the name of the CSV file, so you must ensure that your file name matches your table name exactly. Alternatively, phpMyAdmin provides a visual interface for importing data into tables. On the Import tab, click Browse to select your file. Check that the format and options have been correctly determined from the data file, and click Go. Using this method, you can import up to 2 megabytes of data at a time. You can also use phpMyAdmin to export data from a table to CSV format. On the Export tab, change the format to CSV, optionally specify which rows to export, and then click Go. In this video, you learned that you can use backup and restore functionality at the command line and in phpMyAdmin to populate databases. You can manually insert small amounts of data using phpMyAdmin. And you can use import and export functionality at the command line and in phpMyAdmin to populate tables and save their data to files.
Welcome to Using Keys and Constraints in MySQL. After watching this video, you will be able to describe how to create keys in a table, describe how to use constraints in a table. Similarly to other relational databases, MySQL supports keys and constraints, including primary keys, foreign keys, unique constraints, and null constraints. You can create these constraints either when creating your table or at a later time. In this video, you will see how to create and use keys and constraints in PHP-MyAdmin web interface, a popular visual tool for interacting with MySQL. You can create a primary key on one column or a combination of columns. Primary key columns cannot contain nulls, and the key definition enforces uniqueness on the column or combination of columns in the key. Creating a primary key automatically creates an index on the column or columns that make up the primary key. To create a primary key on a column when creating a table in PHP-MyAdmin, add an index of type primary and then confirm this by clicking Go. If you want to include another column in the key, just add a primary index to that column too. You'll then find a primary key icon next to the column name and an index named primary on the table. Often, your table will have an existing column that fits the requirements of a primary key, such as the employee ID for the employees table. However, in other scenarios, you may want to automatically generate an ID number for each row as it's added to the table. The auto-increment property of a column enables this functionality, and as with keys, can be set when you create the table or at a later time. On the Create Table or the Structure tab, select the AI checkbox for your primary key row and then click Save. Now when you add data to the table, the database engine automatically generates incrementing entries for the input column. You can also create foreign keys to relate data across tables. For example, you can use the input column in the Employee Details table to link the input column in the Employee Contact Info table by creating a foreign key. To create a foreign key, on the Relation view of the Structure tab, enter the name for your key and identify the columns that define it. You can also specify what action to take when a related row is deleted or updated. And as with primary keys, the underlying index now also shows on the Structure tab. By default, when you create a MySQL table in PHP-MyAdmin, the columns are defined as not null. You can change this either when you create the table or by changing the column definition. For example, to enable null values to be entered in the start date and salary columns, select the null checkbox. Leaving the input, first name, and last name null checkboxes blank ensures that those columns require data. To ensure that the email address for each employee is unique, you can use the Unique constraint. On the Structure tab, click the More link for the relevant column, and then click Unique. In this video, you learn that you can create primary keys by defining a primary index on one or more columns. You use auto-increment to automatically generate sequential numeric data in a column. When creating foreign keys, you can define onDelete and onUpdate actions. By default, the columns in the MySQL table in PHP-MyAdmin are not null. You can set up a column to only accept unique values. Welcome to Getting Started with PostgreSQL. After watching this video, you will be able to define PostgreSQL and its deployment options, identify the tools that facilitate connections to PostgreSQL databases, describe specific aspects of PSQL and pgadmin. Postgres is an open-source object relational database management system with a strong reputation for reliability, flexibility, and support for relational and non-relational data types. Postgres is a popular database choice for OLTP, data analytics, and geographic information systems. Let us explore how to deploy PostgreSQL. PostgreSQL offers diverse deployment options, allowing users to tailor their database management to their needs. The first option is downloading and installing PostgreSQL locally on macOS, Unix, or Windows servers. Alternatively, virtualization and containerization provide efficient self-management options. You can install and self-manage PostgreSQL in virtual machine images or containers, which enable efficient resource utilization and scalability. For cloud-based solutions, PostgreSQL integrates with managed services such as Amazon RDS, Google Cloud SQL, Microsoft Azure, IBM Cloud Databases, and Enterprise DB Cloud. Various tools facilitate connections to PostgreSQL databases. Here are a few of them. PSQL is a command line interface, ideal for users comfortable with text-based interactions. pgadmin is an open-source graphical interface for desktop or web applications. It simplifies database management with a user-friendly graphical user interface, GUI. Commercial options like Navicat and dbeaver also provide graphical interfaces supporting PostgreSQL and other databases. Managed database services, such as Amazon RDS, for PostgreSQL, offer web-based consoles and APIs, streamlining database administration in a cloud environment. PSQL is the default command line interface for interacting with PostgreSQL databases. It facilitates connections to PostgreSQL servers through a simple command, allowing users to specify parameters such as username, database, host, and port. Once connected, PSQL transforms the terminal into an interactive shell, supporting real-time execution of SQL commands, including various tasks, from creating databases and tables to performing complex data queries. The tool enhances usability with features like auto-completion and syntax highlighting. The screenshot here shows the library, Postgres user database, and the internal Template 0 and Template 1 databases, which Postgres uses as templates when you create a new database. pgadmin offers a comprehensive platform for interacting with PostgreSQL databases and streamlining development and administrative tasks. Upon the initial connection to the server, pgadmin directs users to the default Postgres database, but as they create more databases, they can switch between them. pgadmin supports many functions, including creating databases and tables, data loading, querying, developing stored procedures and functions, managing database objects, security, and monitoring usage. pgadmin offers the query tool, allowing users to execute SQL commands and interact with the results. The upper pane lets users input or paste SQL queries, displaying the results below. You can use this space to edit the dataset if the results are editable. You can also use the tabs to see an explanation of the query plan, server messages, and asynchronous server notifications in this lower pane. The three important tabs include Explain, Messages, and the Notifications tab. The Explain tab shows the execution plan of an SQL query and is helpful for performance tuning to identify potential inefficiencies. Explain tab example. Query. Explain select asterisk from employees where department equals sales. Output. The output in the Explain tab might show a sequential scan on the employees table, indicating that PostgreSQL will scan each row to find those where the department is sales. The Messages tab displays messages from the most recently executed query and provides feedback on success, error notifications, and other relevant information. Query. Select asterisk from non_existing_table. Output. The Messages tab would display an error message like error, relation, non_existing_table does not exist. The Notification tab displays notifications from PostgreSQL's listen and notify commands. It allows specific database events to send asynchronous notifications. For example, if a PostgreSQL function or trigger issues a notify command like notify my channel, sample payload, and your pgadmin session is listening on my channel, the Notifications tab would display details like the channel name, my channel, the payload, sample payload, and the time of the notification. Additionally, pgadmin incorporates an Entity Relationship Diagram (ERD) tool, facilitating the creation of ERDs for existing databases or generating SQL statements for underlying database objects. To generate an ERD from an existing database, users can right-click and select Generate ERD. The tool automatically reviews the database structure, producing a visual diagram of tables and their relationships. The ERD tool can also help reorganize tables, modify relationships, add notes, and generate SQL statements within the tool, enhancing the overall database design and management experience. In this video, you learn that PostgreSQL is an open-source, reliable, and flexible database system. Deployment options of PostgreSQL include local installation, virtualization, containerization, and cloud services. Tools like PSQL and pgadmin, commercial options, and managed services facilitate easy connections to PostgreSQL databases. PSQL is the default command line interface for interacting with PostgreSQL databases. pgadmin offers a comprehensive platform, including a query tool and an ERD tool for visual design. Welcome to Creating Databases and Loading Data into PostgreSQL. After watching this video, you will be able to identify the steps involved in creating databases and tables at the command line and using pgadmin. Outline the steps to backup and restore databases. Describe how to import data to and export data from tables. As with many RDBMS, you can create databases and tables and load data PostgreSQL by using a command line interface, a graphical user interface, or API calls. In this video, you will see how to perform these tasks using the PSQL command line interface and the pgadmin user interface. You will see how to create the database, then the table, and how to define and edit the columns in that table. Then you'll see how to load data into your database. You can use PSQL to issue commands to create and interact with database objects and data. Use the create database command to create the database and create table for tables, specifying column names and data types. You can use the \d command to show the structure of the newly created table. After you have created the database, you're likely to want to load data into it. At the command line, you can use PSQL to restore a database that was previously backed up using pg_dump. Just specify the name of the destination database and the name of the dump file. This command will recreate the tables, any other database objects, and the data present at the time of creating the dump file. Alternatively, you can use pgadmin to create the same database. pgadmin is a web-based visual tool you can use to work with PostgreSQL. For initiating the database creation process, navigate to the tree view in the left-hand pane, initiate a right-click on Databases, proceed to click on Create, and then click on Database. Enter the name for the new database, and then click Save. If you want to restore the whole database from a dump file, select the database that you want to restore to in the tree view. Click on Restore, and then input the location of your dump file in the Restore box. This step runs the SQL statements contained in that file to recreate the database objects and data in the current database. Alternatively, you can manually create tables using pgadmin. Within the tree view, right-click on Tables, select Create, and then click Table. On the General page, enter the name for your table, in this case, employee_details. Next, navigate to the Columns tab, input the particulars for your columns, and then proceed to save. You'll then see your table and columns in the Tables section of the tree view pane. From here, you can use the Import/Export function to load data into your new table. Within the Import/Export data box, opt for Import, and then specify the location and file name for your data file. If you're loading data from a CSV file, there is no need to specify the delimiter as it's the default option for CSV files. You can then use the View Edit Data option to review the loaded data. This runs an SQL query to display the data in the selected table. Utilize Import/Export function to export current data in your database to a CSV file for external use. CSV stands as the default format, enabling you to simply specify the file name and then click OK. If you want to back up the entire database, you can use the pgdump utility. The syntax of this is similar to restoring data using PSQL. Specify the database name and the file name for the dump file. By default, pgdump creates an SQL file containing a script that describes all of the objects and data in the database. You can customize the command to output to a compressed archive file instead. By default, pgdump backs up the entire schema and data in the database. In this video, you learn that you can use many tools to create PostgreSQL objects, including the PSQL command line utility and pgadmin. You can use pgdump to back up databases and PSQL to restore them. You can use the pgadmin import-export tool to load data into and export data from tables. Welcome to Views. After watching this video, you will be able to describe views, create and use a view, explain how materialized views differ from regular views, create and use a materialized view. A view is an alternative method of presenting information sourced from one or more tables or additional views. You can interact with views in the same way as you interact with tables, inserting, updating, and deleting data as required. Views are a useful way of limiting access to sensitive data, simplifying data retrieval, and reducing access to underlying tables. For example, you could create a view to include the name and email columns from these two tables. Users can then easily access this data without needing to know that it is stored in two different tables and without being given access to the sensitive salary information. In pgadmin, you create views within a schema. So in the tree view on the left-hand side, right-click Views, click Create, and then click View. This opens the Create View box in which you first need to name the view. And then on the code page, you can enter the SQL code that defines the view, and then click Save. You'll then see your view in the Views folder, and you can expand the view to display the columns included in it. To run the view, right-click the view name, click View/Edit Data, and then click All Rows. You'll then see all the rows included in the view. PostgreSQL also supports another type of view, a materialized view. When you refresh a materialized view for the first time, the result set is materialized or saved for future use. This materialization does mean that you can only query the data and cannot update or delete it. However, it also enhances performance for future querying of the view because the result set is readily available, often stored in memory. Creating a materialized view is a similar process to creating a regular view, but you must ensure you start in the Materialized Views folder in the view tree. After entering the name for the view, on the definition page, enter the code to define the view. This example includes just the employee ID and salary columns from the employee_details table to anonymize the salary information. Then click Save, and the materialized view is added to the folder. Because the view stores the data, before using it you need to refresh it with the current rows. And then, you can use the view to access the data it holds. You can refresh the data in the view at any time to update it with the data in the underlying tables. In this video, you learn that views are another way of data presentation from one or more tables. You can use views to restrict access to sensitive data and for easier data retrieval. Materialized views store the result set for quicker access. You cannot insert, update, or delete rows using a materialized view.